So we're going to talk more about confinement and then show how quantum confinement works in more complex heterostructures. And I think this is pretty darn interesting material. I hope you'll enjoy it. Just a quick reminder of some things we talked about last time that are important. One is how useful the energy versus K diagrams are for talking about the optical spectrum. And remember that for a transition to be allowed, the momentum cannot change. For an optical transition to be allowed, the momentum of the starting and final state cannot change. And so if you look at the E versus K diagram of silicon, there are many vertical transitions from the valence to the conduction band where the K value remains constant. But the lowest energy transition, which is the band gap transition in silicon, has two different values of momentum, and that means that that transition is not allowed. And so that gives rise to what people call an indirect band gap semiconductor that has long-lived excited states, is generally bad at photoluminescence, and has a very weak absorption at the band gap energy. And then as you go up in energy and you access more and more possible transitions, eventually you hit an energy sufficient to cause a vertical transition from the valence band to the conduction band. There are many of them, and that steeply rises. So there's the lowest energy region of the silicon absorption spectrum is where all the indirect transitions are, and then they become more direct transitions as you get to higher and higher energies. And silicon still does photoluminescence. It's just weak, and it still does this unallowed optical transition. And those things are actually assisted by vibrations. So if the optical transition couples with the vibrational transition, where both things cause the excitation at the same time, then you'll start to see absorption and photoluminescence. And that makes those transitions temperature dependent. So higher temperature, greater concentration of photons, a wider range of energies, of phonons, of vibrational excited states, wider range of energies, and as a result, the probability of those improbable transitions, the unallowed ones, goes up. All right, and then we started talking about excitons and talked about two different classes of excitons, the Wannier excitons, which are sort of typical for an inorganic semiconductor with a high dielectric constant. These are excitons where the electron and hole binding is weak, and the Bohr exciton radius is large. And so in bulk crystals, these kinds of excitons generally dissociate at room temperature. Their binding is close to thermal energy at room temperature, and so they get thermally excited and the two charges will separate. Frankel excitons are the class that doesn't dissociate because the attraction is very strong. The dielectric constant of the medium in which the exciton resides is small, and that gives rise to small Bohr radii. And so organic crystals like rubrine show this kind of stuff. Metal halides that have a large electronegativity difference and are strongly ionic tend to show this stuff. Excitons with heavy charges, so materials with flat bands, give you localized small excitons that do not dissociate but stay bound. All right, so that's a pretty big difference and it has a really big impact on the way materials behave. I didn't show this slide last time, but it's just a reminder here, clarification. On the left, I've shown an absorption spectrum for an excitonic material. Now, this is meant to be a bulk material. And so an example of such a material is copper chloride. Copper chloride has a pretty large different electronegativity difference. It has relatively weak bonding, and so, or small bandwidths, and as a result, the binding energy of the electron and hole in the exciton is large and the Bohr radius is small. And so you get something that's really got a Frankel exciton in a bulk crystal. And if you look at the absorption spectrum, particularly if you cool the material down, what you'll find is a regular old direct band gap semiconductor type of an absorption spectrum, and then right around the band gap energy, you'll start to see these peaks. And these peaks in the spectrum here, this is a cartoon representation, but these peaks correspond to different Rydberg states, or you may remember from Gen Chem, different orbitals, different orbits of the electron and the hole around one another, or the electron around the nucleus in a hydrogen atom type of a situation. Okay, and so these excitonic absorptions actually appear at lower energies than the band gap energy. Okay, so why? That's kind of a funny thing to say. You have an electron in a hole in this semiconductor sitting in the conduction and valence band, but the luminescence and also the absorption into those states, those various orbits or Rydberg states, is at a lower energy than the band gap energy. So a way to think about this is to remember that the band gap energy doesn't really directly relate to the photoexcitation. It's a measure of the ionization energy or the electron affinity of the material. Okay, and when you have an electron and a hole that are freely moving around in those crystals, when they find each other and they bind to one another, that releases energy. Okay, so before they're bound, the electron and hole have an ionization energy or an electron affinity that is equal to the conduction band edge and the valence band edge. And then when they find each other, they stick and they give off heat in the value of the binding energy. So the excitonic absorption features that you see in that material mean that really that is the promotion of an electron from the valence band to the conduction band, but where the final product remains bound. Okay, and that takes less energy than it does to promote the electron away from the hole and into the free state in the material. So it's the sum of the bulk band gap energy and the binding energy that gives you the excitonic absorption. And this should be a minus sign because the energy of the excitonic absorption is going to be lower than the bulk energy. This is analogous to the HOMO-LUMO transition of an organic chromophore. Okay, when you see an organic molecule and you want to understand its redox potentials and how it relates to the absorption spectrum, you might have some absorption there, and you might know the E1/2, the redox potentials of the conduction band, of the HOMO and the LUMO. And so the energy of the transition is very similar to those, but you also have to consider the binding energy of the electron in the hole in that transition. Okay, so if you know the binding energy, if you know the HOMO-LUMO absorption energy and you know the redox potentials, then you know what's called the binding energy of that exciton in that material. Okay, so let's take another look at a handful of materials we've looked at a number of times, 3, 5, 2, 6, and 4, 6 semiconductors. There are a handful of questions I want to go through down there on the bottom, and to make sure these concepts are drilled in there, let's just sort of survey the results for a second. So notice in the 3, 5 semiconductors here at the top, indium phosphide and gallium arsenide, you have very light electrons, much heavier holes, relatively large dielectric constants, and 10, 20 nanometer Bohr exciton radii. Those are big numbers. Let's go down here to 6 zinc oxide and to cad telluride. All of these have relatively light holes, quite a bit heavier than indium phosphide or gallium arsenide. Same thing in the chalcogenides. The hole state is quite a bit heavier than the electron state. Dielectric constants are a little bit smaller, and the sum of the heavier charges and the smaller dielectric constants gives rise to much smaller Bohr exciton radii. So 1 to 5 nanometers versus 10 to 20. That's a big change. And then down here in the 4, 6 materials, you can see that the masses of the charges are sort of similar. They're in between, really. Um, for lead selenide, they're quite small, similar to a 3,5 semiconductor. But then look at these dielectric constants. The dielectric constants of these materials are very large, and that gives you very large exciton Bohr radii, so on the order of 20 to 50 nanometer Bohr exciton radii. Look over here at these binding energies. So all of these binding energies are small. Remember, 25 uh, millielectron volts is thermal energy at room temperature. Okay, and so all of these materials, if you excite the band gap transition um, in a bulk crystal, you're going to find that the electrons and holes at room temperature readily dissociate. And so if the absorption spectrum of that material is not going to show you any excitonic features at room temperature. Zinc oxide crystals in principle can show excitonic features at room temperature because of that 60 MeV binding energy. All right, so let's take a second here to talk about why the hole is heavier in the 2,6 materials and in 3,5 materials. Does anybody want to provide an answer for that? You can unmute yourself if you like. Why are the holes heavier? Talked about this last time.
They mostly arise from a narrower band.
Yeah, so one of the big reasons is the narrow bandwidth. The hole states in these materials are primarily derived from the chalcogenide orbitals, and those are primarily p orbital states. The conduction bands are primarily s orbital states. Okay, so you have to know the valence orbitals of the two constituent atoms to answer this question. And why do the s orbital states have a wider bandwidth? They have a wider bandwidth because s orbitals make bonds better than p orbitals do. And p orbitals make bonds better than d orbitals do. And d orbitals make bonds better than f orbitals do because of how radially extensive they are. You know, the f orbitals are famous for being kind of contracted. They don't penetrate to the nucleus well because they have a bunch of nodes running right through the nucleus, but they also don't extend out of away from the atom very well. And so they're kind of useless. And so many chemists who are interested in actinides and lanthanides are trying to find whether there's any evidence for f orbital covalency. And there's very limited evidence for f orbital covalency. It happens, but it's generally a weak thing, and the f orbitals are just kind of like buckets for electrons. They don't make they don't do much orbital overlap with adjacent atoms. And as you go toward s orbitals, you get a lot more orbital overlap. There's no directionality. They extend far away from the atom, and so you get big orbital overlap and big bandwidths for s orbitals. And so all those conduction band wave functions, or the conduction bands in all of these materials have big bandwidths, and that gives rise to these small effective masses, right? A big bandwidth is going to have high curvature, low effective mass, big delocalization. Holes, weaker delocalization, and because they have this higher effective mass, and that's because the bonding is not as good. All right. So the other thing is the dielectric constant. And the dielectric constant in these materials, at least the 2,6 and the 3,5 semiconductors, you see a couple, on the order of 3 to 12. And that's a relatively large range, but it's nothing compared to 170 and 250. Okay. So as you go to heavier elements, say the zinc oxide toward cad selenide, you can see the dielectric constant is going up. And that's in large part because the atoms are getting larger, the electrons are further away from the nuclei, and so they become more polarizable on the atomic level. Okay, but how about the lead salts down there at the bottom? Why is that dielectric constant so large? This is not a straightforward answer. Anybody want to venture a guess? How many valence electrons does lead have? Silence. Well, lead is in the same column as carbon. And so it starts out with 4 valence electrons. And now you've made a lead 2, sulfur 2, so a divalent sort of binary material out of lead. And that lead 2 retains 2 of its 4 valence electrons. So lead has a lone pair in this crystal. Lead sulfide and lead selenide are rock salt structures. So the leads and the sulfurs are all octahedral. And this lead lone pair sits in the middle of the octahedron, but it doesn't really want to, it doesn't cost a lot of energy for that lone pair to kind of bulge out and for the lead atom to move around. And so the positions of the atoms in those crystals is not going to be as rigid, because moving off center allows the electron of this 6s electron pair to kind of pooch out, as a coordination chemist likes to say. And that makes those semiconductors very polarizable. So you might remember the long list of dielectric materials, or the table of dielectric materials and their dielectric constants from before. Lead titanate is one of the ferroelectric materials. And it's that motion off center that's helped by this 6s lone pair on lead 2 that makes those materials ferroelectric. Okay, so dielectric constant lead sulfide and lead selenide is large because of that 6s electron pair. So very large Bohr radii, and here we go. So in a few minutes, we're all going to have to log back in. Why does the Bohr radius increase with the effective mass and the dielectric constant? It's kind of a Coulomb attraction problem, right? But it's also a orbital angular momentum type of a problem. And you can look back at the equations for the Bohr radius on the previous slides to answer that. All right, so big difference in these materials and the degree to which they can be confined as a function of crystallite size. Something like lead sulfide and lead selenide feels confined even when you have relatively large nanocrystals. So a 10 nanometer nanocrystal is a relatively large crystal. And if that crystal is formed from lead sulfide and lead selenide, you're going to see strong confinement. If that crystal is Cad sulfide, you're not going to see any confinement because the excitons are smaller than the crystallite size. So for lead sulfide and lead selenide, it's not till you get out to 50 to 100 nanometers before you begin to see that the material is no longer quantum confined because of this exciton Bohr radius, because of that dielectric constant. Okay, so you can guess whether or not a material is going to show this quantum confinement property if you know something about its dielectric constant and you know something about the bonding in that material. All right, so oops. We talked about this Bruce equation. There's our nice picture of Professor Bruce, who formalized this equation. And, he illustrated how the particle in a box confinement potential can be used to talk about the band gap energy in a quantum confined particle. And that the confinement energy is a function of the size or the radius of the particle is related to the bulk band gap and then modified by these confinement and Coulomb terms. So the confinement term is the shrinking particle in a box term, and the Coulomb term is what happens when you force a positive charge on top of a negative charge. The dimensions of that box and the space available to those charges defines the magnitude of these terms here. Importantly, the confinement potential goes as 1 over r squared, and the Coulomb potential goes as 1 over r. And Bruce talked about in his paper how as r approaches 0, it's really this confinement energy rather than the Coulomb energy that becomes dominant. All right, so an important distinction between excitons in a quantum dot and excitons in a bulk material. So in something like copper chloride, where you have these Rydberg states that appear below the band gap energy, you get a spectrum like this. But in a quantum dot, when you take a material that doesn't have a strong binding of the electron hole, say cadmium telluride, there's no excitonic feature. You just get a direct band gap semiconductor absorption onset beginning at the band gap energy. But then if you take that material and you grow nanometer scale crystals of it that are less than 10 nanometers in dimension, suddenly you're going to start to see discrete states, excitonic states, near the band gap energy. And then as the crystals get smaller and smaller, those excitonic states are going to shift to higher and higher energies. And we talked about that in the context of the Buendia figure, which we'll look at here in just a second. But in this case now, instead of these discrete excitonic transitions appearing at lower energy, they appear at higher energy than the band gap. And so I've shown, for example, the 1s, 1p, 1d, 2s, 1f, 2p states, these quantum confined states that you would get in a quantum dot relative to the bulk spectrum. So you get sharp transitions in the quantum dot and broad absorption from the bulk. And you can see the actual data down here for cad selenide, the bulk spectrum here in the dotted line, and the quantum dot spectrum here plotted on top for various sizes. So, you know, remember that each one of these transitions in a quantum dot that you see here, each of the peaks that you see in these spectra correspond to discrete values of K. So here are the different E versus K diagrams, or here are E versus K diagrams for cad selenide. And different sizes of those crystals don't actually change the energy versus K diagram, but they do change which states are allowed in the particle in a box type of a sense, allowed. Which states go to 0 at the edges of the box. Those states correspond to discrete values of K, which are denoted by these circles here on the E versus K diagram. And you see optical transitions from each one of those different K values going up as an integer multiple here, as we talked about last time. So for a smaller crystal, the spacing and energy is larger than for a larger crystal. And so down here you see high energy transitions for small crystallites, and then low energy transitions for big crystallites, but also a decreasing spacing between transitions at large dimensions than at small dimensions. All right, so hopefully that makes the origin of these optical spectra and the meaning of the various peaks at least somewhat clear. You know, the change in the energy, the position of the fluorescence or photoluminescence peaks relative to the absorption spectrum, that should all be relatively straightforward now. Okay, so I want to change gears a little bit and start talking about what I would call more modern quantum dots. These are more interesting kinds of nanocrystals. they are often made of multiple materials. And, you know, people for years have been growing these crystals, optimizing their properties, developing synthetic methods to make them, um, slowly but surely, making higher and higher performance substances. And the interesting thing, the fun in all of this really is not just changing the size, but it's making these combinations of different substances and understanding how the optical properties of the materials change with those compositional variables. There's quite a bit of fun in the synthesis of these materials, which we're also going to start talking about here in a lecture or two. Um, and that's something that my group spends quite a bit of time researching. There's a lot of wonderful things to discover in that space that are not, to describe, that are really not that well understood. And so it's a really fun topic. Technology in this space is really very interesting. People say it usually takes 30 years between an initial discovery and the first technology. There are a lot of examples where this is pretty well documented. Um, and so, back in the 80s is when uh, chemists like Louis Bruce and a number of others started talking about, hey, maybe we should try and make these colloidal nanocrystals to look for quantum confinement effects. And then in about 2010, some of the first technologies started appearing. Um, and that really over that period, there was tons of R&D being done, trying to improve the performance of these materials, studying the size-dependent properties. So we're going to talk about some of the highlights of all of that stuff. Just to explain, so as I was saying, I just bought a television, first TV I've owned in years. And the reason I bought it was that um, the quarantine was happening. Well, actually, no, but thank God we had it for a while everybody was locked down. Um, but this was a TV that had colloidal quantum dots in it, and in fact, um, the latest and greatest televisions have quantum dots that emit red and green light built into them. And there's a bunch of different ways that those devices can be made, but the sort of standard architecture is one where you have blue LEDs, so LEDs that emit a very narrow band blue spectrum, and you actually illuminate a film of quantum dots that emit red and green light. And then you end up with a light source that is red, blue, and green that you can control with pixels in a liquid crystal film or a modulator. And this is just a bunch of different shutters that open and close to let out red, green, or blue light. Quantum dots are great for this task because their emission is bright, they absorb light well, but really it's the tunability, it's the size effect, also composition, as we'll see in a few slides here, that makes the wavelength very flexible. So you can pick whatever emission wavelength you want and get a nice bright luminescence band at that position. The other really valuable thing for these applications is the line width, the narrowness of the peak. And I've shown a handful of example spectra up here in this box in the upper right. Here are some green emitting perovskite quantum dots. Here's a classic phosphor. Probably some of your phones have this potassium hexafluorosilicate doped with manganese. That's this jagged red line here. Here's a red quantum dot spectrum, and then here's a very popular phosphor that's used in lighting applications. It's got this broad line here. To get the blue, green, and red, you mix these various colors together using the filters. And if your light source is very narrow to begin with, then it becomes, that's better for the TV. It can make more colors that way, etc. Okay, so quantum dot TVs are the first application space where this has really taken off. And then the other one is in solid state lighting. So solid state lighting, let's see here, there we are, sorry. So in solid state lighting, what you have is an LED. These are the LEDs that you see all over. Street lights have them, headlamps in cars, flashlights, lights at home, all based on indium gallium nitride devices. So you can see here on the left a photograph of an indium gallium nitride based LED. There's actually two little wires here touching a cup that has the actual crystal inside of it. Um, this thing is about the size of a little pea, pretty small little device. And then if you zoom in further, you can see the cup here. This is one of the wires coming down, contacting this indium gallium nitride crystal, which is this thin yellow stripe here. Labeled in yellow is the gallium in this device. So you drive electrical current through this wire and into this crystal, and then out into this aluminum block. So you drive, half an amp of current through this tiny little flake that's a quarter of a millimeter by a quarter of a millimeter square, and a couple of microns thick. And that crystal streams out blue light, which you can use to make a television, like I showed you on the previous slide, or you can use to make a light bulb. To make a light bulb, of course, you have to convert the blue to other colors. And so you add a phosphor, which is the yttrium in this device. That's this blue powder that's sprinkled into the cup. This is yttrium oxide that has some cerium doped into it, for example, or some other dopant that is luminescent. And so the blue light photoexcites this powder that produces the other colors of the visible spectrum, and it gives you a photoluminescent spectrum like the one shown here in the dashed green line. There's the blue peak from the indium gallium nitride crystal that's doing the work. And then this broad dashed line is the luminescence from cerium, which is doped into yttrium oxide and spans the visible. Now, if you're a light bulb, your task is to make photons and not make heat. And more importantly, in a good light bulb, you can't just make photons, you have to make visible photons. So the photons you make must be detectable by the eye. And your eye has a limitation in its sensitivity. So you can't see in the UV, you can't see in the infrared. And so only photons that come out that are the right colors count for the brightness and the energy efficiency of the device. And typically these cerium emission spectra, for example, have these long tails that spread out into a region where you can't see, okay? And so light bulb manufacturers are very interested in crafting the luminescence spectrum of these devices to only produce visible photons and also to produce the right ratios. So if you have a light source that looks like sunlight, then everything looks natural. If your light source is blue-green, then everything looks cold and kind of ugly. And so the trick is to have these devices take this blue light source and convert it into all the other colors in the right proportions. It's really important for all kinds of stuff. One of the big things is for energy efficiency. 5% of the world's power goes into lighting. That's a huge number. 5% of the world's energy generation is used in lighting. And that little tail that's highlighted in red there, that's lost to invisible photons, is when you integrate over all of those light bulbs, that's like Mexico's annual energy consumption. All the cars and heating of the homes and the light, all of that stuff is contained in that tail. So you're talking about giant quantities of energy, and the crafting of the spectrum of these bulbs is really, really important. So quantum dots are being used in lighting. The world's most energy efficient light bulbs are made with quantum dot phosphors. They have these sharp luminescence bands that are in the red region of the spectrum. And what that does is it allows you to make a warm light source. And this is one of the problems with LED light bulbs. They generally aren't both energy efficient and warm, because it's hard to make red photons in those devices without accidentally making near infrared, unless your red emission source is narrow. And so companies are mixing quantum dots with narrow emission bands to get the color spectrum that they want from their lighting. And as I said, the best, highest performing LED light sources out there right now, based on a single indium gallium nitride color source, have quantum dots in them. So, so let's transition now to talk about why these various materials then are achieve these kinds of properties here, bearing in mind that things like the full width half maximum or the line width of the luminescence spectrum is a really critical performance parameter for something like a display or a light bulb. You want a narrow line source if you can. The other thing that's really important is the photoluminescence quantum yield. Photoluminescence quantum yield is a measure of how many photons are absorbed versus how many photons are emitted. If the quantum dot is very good at absorbing and then re-emitting the light, it's going to have a high photoluminescence quantum yield. And if the photons are absorbed and not re-emitted, then the quantum yield will be low. So why all these different numbers? Why is the quantum yield bouncing around? What's a biexciton? And how does it relate to these nanostructures? All right, so let's take a look at an early and a persistently important colloidal quantum dot diagrammed here in the middle. This is a multi-layered structure. It has cadmium selenide in the middle. It has a wrapper of cadmium sulfide, and it has a final wrapper of zinc sulfide grown on top of that. And this architecture is chosen this way on purpose because the cadmium selenide in the core of the crystal has the narrowest band gap of all three of those materials. And so if you look at the energy level structure of this crystallite as you go from the edge toward the middle and then back toward the edge again, you get something like what's shown here on the left. The conduction band starts out at very high energies in the zinc sulfide region. It drops in the cad sulfide. It drops further into the cad selenide, and then it goes back up again as you transition from selenide to sulfide to zinc sulfide. The same is true with the holes. The spread is not quite as large here in the hole energies. And that's because the valence bands of selenide and sulfide are not that different compared to cadmium and zinc. So this multi-layered structure, what it does is it forces the electron and hole on top of one another in the middle of the crystal, and that gives rise to improved luminescence. When I talk to non-specialists, I often say that the insulating layer on the outside, which has the widest band gap of the three, prevents the charges from escaping. Okay. We're not going to talk a lot about surface states today, or at least I don't think so. But the other job of these layers is to keep electrons and holes away from surfaces. Surfaces are sort of leaky, and they degrade photoluminescence quantum yield. So the other interesting thing that this architecture does is it changes the way in which the electron and the hole interact. And so I've shown the electron and hole of the exciton in this material here, plotted as a radial distribution function. So r squared psi squared versus distance from the center, or radius, I guess. And then it's changes for each of these different materials. So you can see, for example, the hole stays localized in the cad selenide, but the electron actually spreads out into the shell and doesn't so much spread out into the zinc sulfide. So let's just walk through that a little bit here. So I've shown a energy level diagram for cad selenide, this band gap for the semiconductor here, and then the matrix. So this could be cadmium selenide embedded in polyethylene or something like that. So the matrix in which this crystallite sits is going to have a much wider gap. It could be vacuum, although it wouldn't have a spread like this in vacuum, but it's cad selenide in some organic matrix for this example. And I've shown here two different radii of cad selenide, and I've plotted their electron and hole radial distribution functions here. And you can see that the hole decays as you get near the edge of the cad selenide, um, and the electron actually runs into the edge of the cad selenide much more abruptly. Okay, and this difference is a consequence of the electron and hole effective masses. So the lighter the crystallite, the more delocalized it's going to be. And sorry, the lighter the charge, the light electrons in this material spread out effectively over this whole crystallite. The holes, they don't necessarily need that much space because they're fairly localized to begin with. Okay, so you can see that from these radial distribution functions, the electron sort of runs into the edge of the crystallite in both cases, whereas the hole does so, but just to a small extent. And the bigger the crystal, the less these two charges run into the edges. So here's what happens when you add cad sulfide. So cad sulfide, of course, grown on top of cad selenide cores that are 2.3 nanometers in diameter. This whole wave function stays the same. I've changed the axes on you now here a little bit. So the hole sort of doesn't change very much. But now the electron, instead of just running into the matrix, runs into the cad sulfide layer. And the cad sulfide layer can actually accept some of that charge. And then that electronic wave function again runs into the edge of the crystal or the matrix in which it's sitting. And if the crystallite is larger, if the core of that crystal is larger, then the extent to which the electron needs to spread into the cad sulfide goes down. Now, another way to think about this, instead of just thinking about effective masses, is to consider the band offsets. Okay, so here's cad sulfide's gap, and here's cad selenide's gap. And you can see, for example, that the valence bands have a bigger spread in energy between the sulfide and the selenide. There's a bigger difference here. The conduction bands are quite similar. So there is a difference. It costs energy to move an electron from cadmium selenide's conduction band into cadmium sulfide's band, but it's not that great. Okay, so and then if you change the radius of the core from 3 to 2, now this gap changes because you're inducing confinement of electrons and holes in that material, and that's going to push that electron energy higher, and it's going to enable a greater degree of delocalization into the cad sulfide layer. So the junction of cadmium selenide and cadmium sulfide gives rise to this characteristic delocalization of the electron across the whole crystallite, not just the cad selenide core, but the whole tends to be localized only in the core. And now what happens if you grow zinc sulfide instead of cad sulfide? Okay, so this is now a cad selenide zinc sulfide crystallite. Notice down here in the lower left, I've diagrammed the zinc sulfide band gap relative to the cadmium selenide one. You can see that zinc sulfide's band gap is much larger, and the hole really delocalizes into the core. Only the electron will delocalize into the zinc sulfide to a small degree. And if you increase the radius of the cad selenide core, that brings the electron energy level down in the core, and it reduces the degree of the confinement, and so the electron spreads into the zinc sulfide even less. The hole does not delocalize into zinc sulfide much at all. Okay, so the radial extension of these photoexcited charges and their wave functions into the various materials depends upon the energetic alignment of the bands, and it depends upon the masses of the charges, or effective masses of the charges. So there are a bunch of different material combinations that people have explored, and those combinations give you materials that have different properties. Okay, so here's a handful of band gaps diagrammed on the left. So below this bar is the valence band, above this bar is the conduction band. And if you look at any two of these materials, you might imagine combining them to obtain um, different energetic alignments. Okay, and people decompose those alignments into type 1 structures and type 2 structures. So a type 1 structure has a band gap of one material that's nested in another one. So for example, if you look at zinc selenide and zinc sulfide here, the zinc selenide conduction band is lower than the zinc sulfide one and the valence band higher than the zinc sulfide one. So any photoexcited charge prefers to sit on the zinc selenide layer compared to, say, the zinc sulfide layer. The same is true with cad selenide and cad sulfide, as we were talking about in the previous slide. But look, for example, at cad selenide and cad telluride. Now, the conduction band of cad selenide is lower in energy than cad tel, and the valence bands are also offset in the same way. But if you excite this material combination, an electron will transfer to cadmium selenide and a hole will transfer to cadmium telluride. So it actually separates charge. So you can see a list of various materials here: zinc sulfide, cad selenide, mercury sulfide, cad sulfide, zinc cell, cad sulfur, yada, yada, and what their band alignments look like. So cad selenide zinc sulfide is a sort of classic type 1 material where the excited electron and hole really prefer the cadmium selenide region of the particle. Here's one that's inverted. Now, mercury sulfide, which is a very low band gap material, is grown on top of cadmium sulfide, such that the electron and the hole prefer to sit both in the shell rather than in the core. And then there are two example type 2 materials, zinc selenide grown on top of cad sulfide. In that material combination, cadmium is more electronegative than zinc, and so the excited electron prefers to sit on cadmium, which is in the middle of the crystal, and selenide is more electropositive than sulfide. And so if you're going to oxidize one of the two, you're going to pull the electron off the selenide first. And so the photoexcited hole prefers to sit in the zinc cell, in the selenide region of the crystalline. So this type of a structure, when you photoexcite it, the electrons tend to go toward the middle and the holes tend to go toward the outside. And the same is true if you do cad selenide and cad telluride. Now, the telluride is where you want to store the hole, and the cadmium is where you want to store the electron. You photoexcite it, and a charge transfers from the zinc telluride region to the cad selenide region, and the hole does the opposite. People also talk about quasi type 2. Quasi type 2 is where one of the alignments is very similar and one of the charges has a tendency to spread out over both materials. And that leads to partial separation of the excited electron and hole and properties that are kind of intermediate. So let's look at this, an example, cad selenide, cad sulfide. Cad selenide, cad sulfide is the prototypical quantum dot material combination. I've drawn I borrowed, this is a figure from this paper shown in the lower right here, at least part of it. The bulk band gap for cad selenide and cad sulfide are diagrammed here, and the energies of the offsets also shown. And these figures you're going to look at have all considered the same core particle radius of about 1.5 nanometers and a varying thickness of the shell. So now we're going to take this cad selenide and we're going to grow cad sulfide on top of it. And the degree to which we grow that cad sulfide changes the confinement of excitons in the cad sulfide region. It changes the alignment of the conduction in the valence bands then with the cad selenide core region. The smaller the shell, the bigger the confinement, the wider the gap in the cad sulfide, and that changes the magnitude of this offset. So here are radial distribution functions plotted for the hole in this architecture. Again, preferentially rests on the cadselenide and the electron, now spreading out over the whole crystallite. And so this is plotted as particle radius here from 0 to 1.5 nanometers is that core, and the rest of this is the shell, the dimensions of which are given the label H. Now, if you look at the absorption and the photoluminescence spectra of all of these four different crystallites here, what's being done is we're changing how much cadmium sulfide has been grown on top of the cadselenide core. So at the bottom, you have just the pure cadselenide. So 0 monolayers of cadmium sulfide have been deposited. You see the typical cadselenide absorption and photoluminescence spectra right on top of each other. And then as you grow 2, 5, and finally 12 monolayers of cadmium sulfide, you can see the absorption spectrum looks quite a bit different. So down here at the bottom, you get this peak in the absorption that kind of overlaps with the PL. You don't see much of a peak up here. And actually, most of the absorbance is way out here. Now, this happens because these 12 monolayers amount to a relatively thick shell, a couple of nanometers thick shell. And what that means is that the volume of the cadmium sulfide in this nanocrystal is quite a bit larger than the volume of cadmium selenide. So the absorption spectrum for that material is going to look 95% like cadmium sulfide. And way down there in the baseline, you might see some transitions that are associated with the cadmium selenide part of the spectrum. But most of it is a cadmium sulfide absorption. And so you end up with this large apparent Stokes shift between this photoluminescence peak and the absorption onset. But actually, the Stokes shift that you need to be thinking about is the one between this cadmium selenide absorbance, or this one, and that photoluminescence. These guys are still on top of each other. You just don't see a whole lot down here because there's very little cadmium selenide in this final structure. Now, as you change the dimensions of that cadmium sulfide shell, you're going to change this electron hole overlap, okay? And that changes the energy of the crystallite. And, not just the overlap, but the confinement energy of the electron is changing. And so the bigger the dimensions of the cadmium sulfide, the smaller the band gap of the cadmium sulfide, and the lower the energy of the photoluminescence. So you can see the luminescence, which tells you about the confinement of both the electron and the hole, is shifting to lower energy, and it's changing by 200 to 300 millielectron volts, which you can see down here on this scale. So growing a thick cad sulfide shell reduces the degree of confinement of the electron, and it reduces the energy of the exciton luminescence in the structure. The other thing that changes is the probability of the luminescence process, or the rate at which it happens. So people look at how quickly the photoluminescence intensity falls off with time to measure the lifetime of excited states in these materials. And what they find is that an excited state in a crystallite with a large cad sulfide region or a thick cad sulfide shell is quite a bit longer. So about 10 times longer compared to the core material that has no cadmium sulfide grown on it. So growing the cad sulfide onto this quantum dot and making it thicker and thicker and thicker slows down the kinetics of the luminescence process. And that change is really, in large part, about the overlap between the electron and hole. So we're going to come back to this going forward. But that overlap between the electron and hole dictates the rate or the probability of the radiative recombination process. More overlap generally means higher radiative recombination probability. So the changing the dimensions of the shell has a big impact on this electron hole wave function overlap, and that has a big impact on the probability of radiative recombination, or the lifetime here, as shown in these data for these various shell thicknesses. Okay, so the other thing about all those nanostructures that is interesting is that the shapes of many of them are not simple. Some of them are platelets, some of them are rod-shaped crystals, and those different shapes have a big impact on the degree of confinement also. So if you take a bulk semiconductor and you say, all right, let's confine charges in that bulk semiconductor along one dimension, what you get is a platelet or a very thin crystal. And if you confine in 2 dimensions, then you get a rod or a wire. And if you confine in 3 dimensions, then you get a quantum dot or a nanocrystal. And so if you look at the energies of the conduction and the valence band of the bulk material, and then as you go toward the nanoplatelet, the rod, and the quantum dot, what you see is the density of states goes from smooth to kind of blocky to spiky to discrete. Okay, so in the quantum dot case, the wave functions that you can get for the particle in the box confinement picture must truncate in all 3 directions to provide a solution. And so there's only one solution at each value of k um, in the E versus k space, and you get these discrete transitions in the or discrete states in the electronic structure. In the case of a wire, it's not confined along this long dimension, or a rod, it's not confined so much along the long direction. And so you don't get discrete states in that along that direction. You only get them along the x and the y dimensions. And then the platelet, it's just uh, the thinness direction, and otherwise the crystal looks infinite. Okay, and so that gives you this very interesting evolution of the density of states diagrams, and that has another big impact on the many big impacts on the recombination kinetics. So for a long time, people have been looking at this, studying this, and have realized, wow, I can make a quantum dot out of any material combination I want, and I can get the charges to be on top of each other or separated, and maybe I could make a great photocatalyst out of that, or maybe I could make a better solar material that way, or maybe I can make something that's very brightly luminescent for lighting applications. And so people have made all kinds of wacky structures, some of which are rod shapes that have little peanuts on the end. Sometimes you get seated things with a material, one material with another material grown on top of it in 2 directions or in 4 directions, and so on and so forth. So there was kind of like a gold rush for a while of what kinds of different quantum confined nanoparticles could I make and what would happen if I combined them. And people kind of turned the crank on this idea for 20 years or something like that. So let's just look at 2 examples of this kind of thing. Uh, one of them is the quasi type 1 situation where you have cad sulfide grown on top of cad selenide, and you have this gap for the cad selenide seed here, and then you have the gap for the cad sulfide region. And this is really a quasi type 1 because the electron and the hole both prefer the cadmium selenide, but the electron will actually delocalize over the entire rod because of the similarity of the band gap alignments in the structure. Now, another variation on this theme is a zinc selenide seeded cad sulfide rod, another pretty cool structure. In this case, zinc and cadmium have very different um, electronegativities or electron affinities. And so when you photoexcite this material combination, the hole localizes in the selenide and the electron delocalizes in the cadmium. And so now you get a large separation between the photoexcited electron and hole. So the rod situation looks an awful lot like the core shell case, except the length of the rod now defines the degree to which the electron and the hole overlap with each other. And so the degree of confinement in that long direction is not very strong, and it has a minor impact on the energy of the exciton, but it can change the electron and hole overlap fairly substantially. So people plotted here on the upper left is the electron hole overlap versus the arm diameter. Oops, not the length in this case. But you can see that as the arm diameter, sorry, the diameter of this crystallite here gets larger and larger, the electron spreads out more and more, and the electron in the hole overlap less and less. And you can also see here the absorption spectrum, which is primarily cadmium sulfide. Way down here in the baseline is the cadmium selenide region of this absorption spectrum, on top of which the luminescence band rests. So same as before, cad sulfide does most of the absorbing here. Cad selenide does most of the emitting, and the arm dimensions impact the electron hole overlap and change the recombination probability. So here's a slightly different architecture. This is one where now we've grown, just check and see what time it is here. Sorry, I don't have my So here's an architecture now where we've taken cad telluride and we've grown cad selenide onto it. So this is very similar to the seeded rods that we looked at before, except it's a type 2 situation. So in this situation, the hole prefers which material? Does anybody want to guess? The diagram tells you. The hole prefers to go to the more electropositive valence band, and that's the telluride. Telluride is more easily oxidized than selenide. And the electron also tends to localize on the cadmium selenide. Its conduction band is lower in energy. So when you photoexcite this type 2 heterostructure, now the electron goes to the cad selenide, the hole goes to the cad telluride, and this charge separated state people sometimes refer to as a charge transfer exciton. So this is the product of photoexciting a type 2 material. Now, these electrons and holes are really well separated. They have very low overlap. And so the luminescence lifetimes are very long, maybe as long as a microsecond. Okay, microsecond's a pretty long time. And these are quite a bit longer than the simple cadmium sulfide, cadmium selenide material pair. And so if you look here, for example, at the cadmium selenide absorption spectrum and the cad selenide, cad telluride absorption spectrum, you can actually see a small amount of luminescence that comes from cad selenide alone. You can see a small amount of luminescence that comes from cad telluride alone. And then you see finally out here at much lower energies, what is labeled as charge transfer photoluminescence. Charge transfer photoluminescence comes from the recombination of the electron and hole with each other after they have separated into the two different materials. Okay, so the electron is sitting in the cad cell, the hole is sitting in the cad telluride, but they can still undergo radiative recombination, and the energy of that band is shifted to lower energies compared to recombination from the pure materials. And so this is sort of an example of type 2 photoluminescence behavior. If you photoexcite this thing, either by pumping a region where cad selenide absorbs, you create a pure cad selenide exciton, or if you excite only the cad telluride region, which is at lower energies, you might get an electron hole pair there. And what happens after that initial photoexcitation is that the two charges separate. Okay, and they sort of separate right at the junction, but they still have some attractive potential, and so they bind to each other across that junction. Now, if the binding is relatively weak, then you can dissociate it thermally and make the charges go to different regions of the spectrum and produce free carriers in this sense. Okay, and so the radiative recombination from this structure depends upon the strength of this interaction, the degree to which the charges overlap, and the concentration of this bound state from which the photoluminescence process happens. And so um, the temperature dependence of this luminescence reflects that higher temperatures reduce the recombination probability for this reason.